Now, if we look at the environment, then there are a few things that we need to take into account. First is the acceleration of gravity. You can see that the moon is 17%, has 17% of the gravity of the Earth, whereas Jupiter is the acceleration of gravity is 2.36 times that of the Earth. So there is a range of acceleration of gravity, and of course, if you have zero gravity, then there is no gate. Right? You cannot do any motion at all. So this is something to take into account. Then we have topographic features like slopes, mountains, craters. You can see here, which is important. These restrict the gaits that you can have and the speeds that you can have. You can have also special characteristics like rocks, pebbles, and so on. And secondary effects like weather conditions, which can be modeled as external disturbances, and corrosion radiation, which can be modeled as changes in the mass of the system. Now the question is, what is the effect on the gaits that you can get when these conditions are valid? So we are interested in looking at the apex height and the stride length, the dynamic stability, and the contact and impact dynamics of our robots in the presence of these conditions. Now, if we look at the contact dynamics, which are quite important, then one can find a lot of literature on terra mechanics, but most of this work is related to wheels, wheel-soil interactions, and high speeds. And these do not apply here because the speeds are not that high, and we have legs. So we can look at alternative models for the interactions, and one can assume rigid body models, which are applicable only when the soil is extremely rigid. You can go to finite element methods, but these take a lot of time and are not good for control or for even running the simulations. So viscoelastic models tend to be the best option here. So to use the viscoelastic models, we use nonlinear springs and dampers. And if we had, say, linear spring, this is a force and this is displacement, we would get a straight line here for a linear spring. When it's nonlinear and it's, say, we use the Hand-Crossley model, then we get this curve. So here it's compressing the earth, the soil, and then decompressing. But this is the energy lost in the cycle. The problem with this is that it goes back to zero, which means that you compress the ground and then you let it go, and the ground goes back to where it started from. But this is not what is happening in reality. So we devised a new model, and with a parameter which is lambda. And based on lambda, you can start compressing the ground, but then you can come to this point, and the next compression cycle will start from this point, and so on. Even this, though, takes a lot of time when you have to do a lot of simulations. So in some cases, it's better to use an equivalent stiffness or damping, assuming that you have a spring and damper for the leg and the same for the soil, and you get the equivalent spring and damper. So how do we classify gaits? We use the Hildebrand gate diagrams, which are shown here. And here you see the left legs and the right legs. And this line is the percentage of time during which the leg is on the ground. So this is 100%, and this goes up to 48%. So this is the left back rear leg, this is the left front leg, and so on. And based on the diagram that one gate produces, we can classify it according to, say here, bounding and pronking. The difference between these is that this time difference, the difference between rear and front contact times. So if this difference between, say, the left front leg and the right front leg this difference here is, if it's less than 3%, then we call the gate pronking. And in pronking, we'll see it later. I'll talk about this later. If this difference is higher than 3%, then it's bounding. In terms of optimizing the gates, this is our optimization vector, and this includes a number of variables and parameters. These are the gate parameters, which include the forward velocity of the center of mass and the apex height that the gate achieves. If this apex height is higher, then you can go over bigger obstacles. If the velocity is higher, then you go faster, of course. The initial conditions at which are needed to get to this gate. This includes the initial center of mass forward velocity, initial height, and initial pitch rate. And these are design parameters, like the spring constant of the legs. This is the uncompressed length, and this is the hip joint distance, which essentially tells you how big your robot is compared to the legs. So the objective function that we used is, in a sense, takes into account the mean power consumed by the robot in those gates. And we have constraints, like the torque cannot exceed this amount because of technological reasons. And we employed a number of techniques. The F-mean con from MATLAB Simulink, which is a constraint optimization algorithm, and the differential evolution algorithm. Now this plot here shows some of our results, which come from an extensive search. This is a very dense result. It shows both the effect of planets and the effect of one of the system parameters of the spring constant. So you can see that, first of all, if the spring constant increases, perhaps I should say that before doing this, I should say that this axis here indicates the phase difference, and this one here indicates the amount of time where the mean legs, the mean duration of the legs corresponds to the time at which the legs stay on the ground. But this is a mean, because one leg may stay more and the other one may stay less, so we take the mean. So this is time on the ground, and this is difference between legs. So with this we can classify the gates. And if you see here the 3% limit, so if you get points above this limit, you get pronking. Below this limit, you get bounding, different types. So now as this is Jupiter, and as we go to the right, the gravity decreases, so we get here to the moon. And so you can see that as the gravity ratio becomes higher, for example, we go this way, then the duty factor increases. Duty factor is here 0 and goes this way. So going like this, increasing, going to bigger planets, the duty factor increases. If we look at springs, then stiffer springs means that we go this way, and then as we go this way, the duty factor decreases. So we can have a picture on just one gate graph on what are the effects of different planets and different design parameters. So another result here is that what happens when you have slopes, and when the robot is trying to overcome slopes at 0, 5, and 10 degrees, the gate graph is the same. So as you increase as you go from 0 to 10 degrees, from here to there, then the phase difference here increases, and the gate becomes more bounding-like. If the slope is 0, you can achieve some pronking, but not bound. So if you increase the K, again you get the similar results like before. So that means decreased duty factors, which means that the legs stay on the ground for less time, because the system is more stiff, so it hits and goes away quickly, whereas If the springs are soft, it stays for more time, just smaller motion. Okay, so to conclude this brief introduction, we have seen that legged robots can be used in space exploration. We have modeled quadruped dynamics and the ground behavior that is related to these robots. We classified the robots using the Hildebrand diagrams, and then we studied the effects of leg stiffness, gravity, and ground inclination using the gait graphs in extensive searches. The methodology that we used, which includes the optimization for the gaits, can be used in identifying the optimal gaits. So given a planet and a system, which is the best gait for it. And it can be used also in designing improved quadrupeds for planet exploration. That concludes my introduction. Thank you.